Okay, we're going to talk about addition polymerization in this lesson, and it's something you've done already at GCSE, so it's more of a reminder really what's going on there. Right, what I've drawn there is I've drawn 4 ethene molecules, and really I should have drawn thousands of them, but obviously can't be bothered doing that. And what happens is those double bonds break, and you form a new bond between those 2 carbons. Breaks, new bond, breaks, new bonds, and so on. And what you're going to get is you're going to get a big long line of carbons, each one with 2 hydrogens attached to it. I'm not going to draw the hydrogens because it would take too long. Okay, and that just means it carries on sort of forever. There'd be a few thousand ethene molecules long. Okay, so this is called ethene, and the recommended name for the polymer is just the same as the monomer with poly put in front of it. So this is polyethene. Now, you wouldn't normally draw the reaction like this because it takes a long time. So what you'd probably do is use a shorthand. So you'd write down, you've got N molecules of ethene, and they are going to react to form polyethene. So you just draw, this is called one repeating unit, and you put a bracket there going through those bonds, and then N there to show there's lots of them. Okay, and that's polyethene. What can we say about polyethene? Right, so we're going to say, right, ethene is a gas, isn't it? Polyethene, as we all know, is a solid. And why is that? It's because it's a much bigger molecule. So you've got more points of contact, more van der Waals forces, stronger van der Waals forces, so it's a solid at room temperature. It is also, these addition polymers tend to be fairly unreactive. And that's good in a way, but it's bad in a way because it means they are non-biodegradable. I think the reason why they're unreactive is because you've just got loads of carbons and hydrogens, and there's no polar bonds there, so there's no possibility of nucleophiles attacking there, and the resulting product is very unreactive. Okay, so we can have slight variations on polyethene. So for example, if we have they have this molecule, which is called, there's 4 fluorines there, so it's called tetrafluoroethene. And when it polymerizes, you get N of that lot. You're going to form, so the polymer is going to look like this. And that is called Teflon. Its proper name is polytetrafluoroethene. Its kind of trade name is Teflon. Oh, thanks very much. Cheers. Thanks a lot. See you tomorrow. Bye. So that's Teflon. And as you know, Teflon is found on non-stick frying pans. It won't catch fire because the carbon-fluorine bond is very strong, and so there's no it won't burn. Another example which we need to know about is the polymer is called PVC, polyvinyl chloride, which is actually the old-fashioned name for it. Okay, it's not the non-new pack name. Polyvinyl chloride is made from chloroethene. And that polymerizes, and so the polymer is going to look like you're going to get alternate carbons have a chlorine atom attached to them. So that's called chloroethene. The old-fashioned name was vinyl chlorine. And the polymer is polychloroethene. And the old-fashioned name is PVC. Now PVC is a bit of a stronger polymer than polythene. I think one of the reasons why you've got chlorine there, it's bigger, it's got more electrons, you can get stronger van der Waals forces. The PVC is more of a robust polymer than polyethene. What we also need to know about, a kind of molecule called a plasticizer. Plasticize, I haven't spelled that right. Now, what are these? These are small molecules which are mixed with the polymer and they reduce the strength of the van der Waals forces between the chains, and so they make it more flexible. Now, depending on how flexible the manufacturer wants the plastic to be, the PVC to be, you can add larger amounts of plasticizer that will make it very flexible, not much plasticizer that will make it more brittle and less flexible. You just have a very basic understanding of how plasticizers work. So this is going to be my PVC chain. Okay, so imagine that's PVC, polymer chain. All right, that's with no plasticizer. So all of those molecules, all of those polymer chains can get fairly close together. You're going to get strong van der Waals forces. So it's going to be brittle, inflexible. If you add the plasticizer, then what happens is, so I'm going to draw the plasticizer in red. These are small molecules. Just draw a few of them about here. So what tends to happen is they mean that the polymers, they can't form such strong interactions with each other because they disrupt the van der Waals forces. And so they make the plastic more flexible. Plastic is softer, more flexible. And you probably experience this if you get really old plastic things like a watering can that's been left out in the garden for about 5 years. It gets very brittle, and I think the reason for that is these small plasticizer molecules. They kind of need to do so thick as that. These small plasticizer molecules, they will kind of evaporate gradually out of the plastic, leaving behind just the polymer. It makes it brittle. Okay, so I think that's all we need to know about addition polymers.